class. Today we're going to be doing section 5.18 in AP Stats, which is all about confidence intervals. Today we're going to be looking at confidence intervals for proportions. Now today will be a little bit of a longer video, so I'm going to try to go fast. You'll need to pause the video and write some stuff in on your own time, but it's a pretty long section. So here we go. Marine scientists fear that pollution, global warming, and increased acidification of the oceans are destroying the world's reef system. They want the proportion of all reefs that are currently dead to have a baseline for future comparison. Unfortunately, it is impractical, if not impossible, to analyze every single reef on the planet. So a sample survey determined that 54 of 104, or 0.519 or 51.9%, randomly selected reefs were devoid of life. So is it reasonable to conclude that 51.9% of the world's reef system is dead? Well, no, it is not reasonable to conclude that 51.9% of the world's reef system is dead because sample results can vary. Just because we took one sample of some reefs, 104 reefs in the planet, doesn't mean that every sample would look exactly the same. And it doesn't guarantee that the one sample we grabbed is even representative of all the reefs on the planet. You have to find lots of samples in order to be confident in that. Do you expect a second sample of 104 randomly selected reefs to also have 51.9% dead? Again, no. I would not expect that because sampling variability says that it's just natural that each sample is going to vary from other samples, especially when they're randomly selected. There's just no telling that one sample is going to be exactly the same as the other. So we wouldn't see the exact same percent of dead reefs. Now, it is technically possible, just highly unlikely. The scenario above highlights why a single sample statistic, such as p hat, is not commonly used to estimate a population parameter, for example, p, since it's highly unlikely the sample statistic is equal to the corresponding population parameter value. Rather, researchers create an interval of values in which we have a certain level of confidence that the population value is captured within the interval. So confidence intervals is used to estimate the population parameter. So again, population parameter in this case would be P, which is the true proportion of whatever we're looking for. So the confidence level in percent of a confidence interval indicates our degree of faith or confidence that the interval captures the true or population value. A confidence interval is centered around our sample statistics. So when we take the sample of 104 reefs and we find that 51.9% of them are dead, that's our p hat. So we're going to center our interval around that value, so 51.9, and then we're going to say, but it might be, plus or minus some sort of margin of error. So it extends, so we've got p hat in the middle and extends a given number of standard deviations in both directions to account for the fact that sampling variability, my sample might not be perfect. There's a certain level of error that we are pretty sure is all right. Our sample's not exact, but within this interval, we should see the true proportion. All right, so the next page here, confidence intervals and the sampling distribution of p hat. So we need to use the properties of sampling distributions of p hat, which we did in our previous lesson. So if you haven't watched that, go back and watch it. Since confidence intervals are based on sample sizes greater than 1. Therefore, the confidence interval to estimate P is P hat plus or minus some critical z-score, so we call that z critical, times the standard deviation of P hat. So where z with the little asterisk is called the critical value. Now, on your AP Stats formula sheets, there are confidence intervals. It's on the first page, actually, and it's down here. And it doesn't give the exact formula like we see it here because we can have confidence intervals for proportions or means, but it says the statistic, and remember, our statistic is p hat, plus or minus the critical value, in this case is z critical, times the standard error of the statistic. And then if you go to the next page, it tells you what the standard error of the statistic is going to be, depending on if you have proportions or means. So you can see that here. So you can piece together the formula from this this document, but you definitely need to know where to look and how to do that. All right, so unfortunately, we have unfortunately, what is the major problem preventing us from calculating our standard error? Well, we do not know the value of P. So if we knew the value of P, we wouldn't need a confidence interval to estimate what P is, right? We would just say, well, that's P. So the whole point of a confidence interval is to take a sample statistic, P hat, and estimate what the true value of P is. So we will never have P if we're doing confidence intervals, or we would not need to do the confidence interval. So in this case, and this case only, we are going to use P hat instead of P. Whenever we estimate the standard deviation of the sampling distribution, we call it a standard error. Thus, the standard error for a confidence interval to estimate P is, so standard error of P hat is going to be the square root of P hat times 1 minus P hat over N. So same type of formula, just with P hats instead of P's. For the specific example regarding estimating the proportion of the world's reefs that are dead, the standard error, so standard error of our P hat would be the square root of 0.519 times 1 minus 0.519, which is 0.481, divided by 104. That was our sample size. So we would get 0.049 as our standard error. Based on our empirical rules, so oh my gosh, think all the way back to our first unit or two, we have the 68, 95, 99.7 rule when it comes to normal distributions. 95% of the reef samples will have a dead proportion within 2 standard deviations of the true proportion of dead reefs worldwide. So remember, within 2 standard deviations, you have that 95% in there. Theoretically, the P hat from our single sample will be no more than 2 standard deviations away from our true proportion. Thus, it's reasonable to be 95% confident that the interval from our P hat plus or minus 2 standard errors contains the true proportion of the reefs that are dead. All right, and you can see I kind of drew that Z curve here, our normal curve, and within 2 standard deviations, we have that 95%. Now, interpreting a 95% confidence level. So we're going to do 2 different types of interpretations here. We're going to interpret the confidence level. We're going to interpret the confidence interval. Every time you make a confidence interval, you need to write the interpretation of it. And we're going to practice that today. If it specifically says interpret the confidence level, they simply want you to say what the 95% means, not in terms of your problem exactly. So formally, a 95% confidence level means that about 95% of the samples of a specific sample size, sample size will produce intervals that capture the true proportion. That's it. So, for example, if I constructed 100 confidence intervals that were generated from 100 different samples of the same size. So let's say that we have our first sample of 104 reefs. We took that sample of 104 reefs, we got the proportion P hat. Now, if I take another, and then from that P hat, we made a confidence interval, 95% confidence interval. If I take another sample of 104 reefs, I get a new P hat. I make a new confidence interval. It's not going to be the same as my other one. Then I take another sample of 104 reefs and so forth, and we get intervals for each one of those samples. They're not all going to be the same interval. In fact, most of them are going to be different intervals, but 95% of those intervals we constructed will contain the true proportion. That's what the 95% confidence level interprets as. Okay, note that interpreting a confidence level is not the same as interpreting the specific interval. Now, for my students, on the next page, there's a little exercise where you go over incorrect ways to interpret the confidence interval. We are going to skip that because this video is already going to be pretty long. So you can ask me about it in class if it doesn't make any sense. All right, so let's look at constructing a confidence interval. So confidence interval for P can be computed by using P hat plus or minus our Z critical value times the standard error for P hat which is p hat plus or minus z critical times the square root of p hat times 1 minus p hat over n. Z little star is called the critical value, and it indicates the number of standard errors. So square root of p hat 1 minus p hat over n added and subtracted from p hat. This is known as the margin of error. So that margin of error term, you're going to need to know that. It comes up quite a bit. They'll reference the margin of error. You need to know what that means. And the margin of error is this amount. This is margin of error. So it's whatever you're adding and subtracting from your p hat. That's your error. So plus or minus some margin of error. Note the critical value is always positive. So always positive z-scores since it indicates the number of standard errors. Now we have required conditions. So pretty much from here on out, everything in AP Stats, we have conditions that need to be met before we can do anything. Luckily for you, these are the same as our previous lesson. So a lot of them overlap. We have our independence condition, our randomization condition, and that our sampling distribution of p hat needs to be approximately normal. Also, you want to make sure you name the type of confidence interval that you're running. So we talked about that before too. It's important to name what we're doing. So I like to name it. The first thing I do is I say conditions for, and I name what I'm doing. All right, so before we get there, example. A random sample of 250 AP Stats students found that 32% of the students earned an A on the Unit 5 exam. What is the point estimate for P equals the true proportion of AP Stats students who get an A on the Unit 5 exam? So point estimate is what's the estimation for that P value? That's our P hat. And that's 0.32 because that was our sample proportion. So that's what they mean by point estimate. Now construct and interpret a 90% confidence interval for P. So from our 250 randomly selected AP Stats students, we found that it's 32%. But if we selected a different 250 AP Stats students, it might not be exactly 32%. It might be something else. Or if we did another one, it might be something else. But we're going to find an interval based on our one sample where we can be 90% confident that the true proportion of, or the population proportion of AP Stats who get an A on their Unit 5 exam is within that interval. Conditions. Number one, 250 AP Stats students is less than 10% of all AP Stats students. So independence is assumed. There's our 10% rule. You could also just say that it's reasonable to assume that one AP Stats student isn't going to affect the next based on context, but I like to use the 10% rule if I can. Number two, it's stated that a random sample of 250 AP Stats students. So we have a random sample. It was stated that it was random. So we want to state that. If it's not stated that it's random, remember, you can just say that you're going to assume that the sample was not biased and thus is a good representation of the population of AP Stats students. We don't have to do that if it states that it's random. Number three, N times P hat. Now remember, this is usually N times P, but we don't know P. We're doing a confidence interval because we don't know P. So we have to change everything P to P hat for confidence intervals. So N times P hat is 80, which is at least 10. N times 1 minus P hat is 170, which is at least 10. So it's important to write the next part. You don't get credit. Sample size is large enough to assume the sampling distribution of P hat is approximately normal. Now let's do some math. So we have our P hat value, 0.32, plus or minus the Z critical value. So now I'm going to show you how to do this. I want 90%, and I need to find the Z critical value. So you're going to go to your formula sheet. You're going to go to the T distribution. So the T table, it's right below the Z table. So we had our Z tables here. Keep going. It's the T table. Now, I know we haven't used this yet, and I'll explain how to use it later. You don't need to know yet. Just go all the way down to the bottom of the T table, and it tells you the confidence level, and above that has the percentages. And right above that, see the little infinity on the left-hand side, on the leftmost column? That represents the Z critical score. No, it doesn't say Z critical, but that's what it represents. So 90% confidence level represents or has a Z critical score of 1.645. So directly above 90%, we see 1.645. All right, so that's going to be 1.645 for 90%. So I'm going to put that in there. So 0.32 our p hat plus or minus our Z critical value times the square root of p hat 0.32 times 1 minus p hat 0.68 divided by our sample size of 250. That's going to be, well, we can plug that in our calculator. So we get the interval from 0.271. So if I take 0.32 minus our margin of error, all the way to 0.369, which is 3.32 plus our margin of error. So there is our confidence interval, which means I am, and this is how to interpret the confidence interval. So this is our first interpreting the interval piece. And there's kind of a script that I've written out here with some context, and we need to fill in these blanks. So I am 90% confident that the true, or you could write population, proportion of AP Stat students who scored an A on the Unit 5 exam is between 0.271 and 0.369. And that's it. That's a whole confidence interval problem. All right, I'm going to skip example 2. Just a quick note, and I talked about this last time. If it says assume all conditions are met, you can do your little happy dance, but you also need to write a statement. You need to write that it is stated to assume all conditions are met. And then because I'm not writing the conditions, sometimes it's easy to forget to name it. So you still need to name it confidence interval 90%. Actually, I usually write 90%, or in this case, I need to read 95% confidence interval for P. And then you can do all your math and your interpretation and things like that. I'm going to skip it because we have more things to do. All right, example 3. How does increasing the following factors affect the width of the confidence interval? Answer wider or narrower and support your response. So if I increase the confidence level, so go from 90% to 95%, for example, our interval is going to get wider. Think about it this way. The wider the interval, the more confident I am that the true proportion is in there. So I increase my confidence when the interval gets wider. I'm more confident that it's in there. If I narrow my interval, I'm less confident that the true proportion's in there because it could be over here or something. So the wider the interval, the wider the confidence level, the wider the interval. Increasing the sample size. So now if I have a larger sample size, it means my values are more precise. They're more consistent. The standard error decreases. Thus, our interval is going to be smaller. And decreasing our p hat value from 0.5 to 0.1. So if we think about the formula for a standard error, p hat is in the numerator. So as that decreases, the standard error decreases, and thus the interval becomes more narrow. All right, last example. Look at that. I'm getting there. Okay, example 4. A study wants to investigate if cats can be used to detect drugs. How many trials must be conducted to produce a long-run proportion of cats who can correctly detect drugs within 0.03 with 90% confidence? So kind of a silly little example. A couple of things I've already written out here. If I have 90%, my Z critical score, again, we use that T table, go all the way to the bottom, Z critical would be 1.645. The margin of error, so it says within, I want to calculate the proportion of cats to within 0.03. So that's our margin of error. So margin of error is 0.03, and that's the part of the formula after the plus or minus. So I can take that formula, Z critical times my standard error of P hat and set it equal to 0.3. But if you notice, I'm trying to find N. So N equals what? But I don't know P hat. And I can't solve one equation with 2 unknowns. I need to know P hat. So, oh no, if we don't have P hat, it's okay. we can actually just assume that it's 0.05 or sorry, 0.5. We only do this in this scenario when I'm trying to find how many trials I need and I don't have my p-hat because I haven't run my trials yet. Then we just assume that it's 0.5. It's one of the only times we really do that. Okay, so now we can calculate this. So we've got 0.03 equals 1.645 times the square root of 0.5 times 1 minus 0.5, which is 0.5, over n. And then I'm just going to do some algebra to figure this out. So first we divide 0.03 divided by 1.645, and I get the square root of 0.25 over n. And then I'm going to bring my work over here. I can square everything. So 0.03 squared over 1.645 squared equals 0.25 over n, because I squared that square root to get rid of it. Then n equals, so if I multiply both sides by n, actually, well, I mean, it's a proportion. So you can kind of switch diagonals, multiply, cross multiply, and divide. So n ends up being, let's see, we've got 1.645 squared times 0.25. So multiplying that diagonal and then dividing by our 0.03 squared, which is multiplied by n when I do my cross multiplication. I get 751.674, which means I need at least 752 cats to be confident. Specifically, 90% confident to within 0.03. So my margin of error, 0.03. All right, and I believe that does it for today's lesson.